Welcome back everyone to part 4 of our full ANN regression code along. What we're going to go ahead and do here is create an instance of our model, and then we'll go ahead and define the loss function and optimizer, perform train test splits, and train our model. Let's get started. Okay, here I am at our model. We have the tabular model set up. Let's go ahead and create an instance of it. To start off, to make sure you get the same random initializations I do, go ahead and say manual seed of 33. And again, 33 is an arbitrary number choice. And let's create an instance of this model. We'll say a tabular model here. We pass in the embedding sizes we defined earlier. And next we need to say, well, how many continuous features do we have? And from that we can just grab continuous shape, index at 1, since the 0 indexes the number of rows. Then we want to define the output size. Well, the output size, recall, is going to be the output for regression is just 1 because we're predicting a single value. And then for layers, which is the next one, so layers is the next one, we can define a list of how many neurons we want per layer. So you can say 200 in the first layer and 100 in the second one. Again, that's something you can experiment with. And then the probability for that output layer, or dropout layer, excuse me, can be 0.4. So we go ahead and run this and create our model. So when you see your model, you have this tabular model here. And here we have the normalization occurring on the 200 features. So you can say in features 23, 200, and then in the next layer, it's coming in with 200, coming out with 100, and the very last one is coming out with 1. So it's up to you to experiment with these layers, but this is what we use in the lecture notebook, and we got pretty good results with it. So we'll go ahead and continue. Next, we want to define the criterion and optimizer. The criterion we'll use here is NN mean squared loss, and we'll convert this to root mean squared error later, because recall that if you just take the square root of the mean squared error, that gets you root mean squared error. And then finally we'll say optimizer is equal to torch optim atom, pass in the model parameters just as we did before, and then you can define your learning rate. For the lecture notebook, we went ahead with a learning rate of 0.001. If it takes a long time to train, which it kind of already does, you should expect this to take at least 30 minutes or more of training time if you intend to train it on all the records. You can try learning at a faster rate, but we found good results after kind of 30 minutes or more of training with 0.001. So if you want to follow along exactly with us, you can choose that learning rate, or you can kind of play around with it. You can also play around with the number of neurons if you want to try to reduce training time. Okay, so next we want to perform the train test splits. So at this point, our batch size is the entire data set at 120,000 records. That's going to take a really long time to train. So let's go ahead and consider reducing it. Let's make the batch size, cut that in half, like 60,000. So we'll say our batch size, we'll feed it in 2 batches. So we'll say 60,000 here, and then our test size is going to be equal to 20% of the batch size. So we'll say batch size times 0.2 for 20%, and we don't want that to be a float since we're going to be using it for slicing in just a second. So we'll go ahead and push it to the nearest integer. And then we're going to have training sets for both categorical and continuous. So we have our categorical training and test, and then our continuous training and test. So we're separating out both of these separately because we have them right now separate. So then all we need to do is recall we can do this because all our data was shuffled already. If that wasn't the case for your data, you want to go ahead and shuffle it before you do any sort of separation of categorical variables or continuous variables. So for this, we'll just say cats, starting from the beginning, for batch size minus the test size. For cat test, we'll say cats, going from the batch size minus the test size, all the way to the batch size, just doing some simple slicing here. For the continuous, we'll say continuous, and just essentially going to copy the code here. So batch size minus test size, starting at the beginning, go all the way to that. And then for continuous, same thing here for the test. Okay, so this is our train test split, and we need to do it again for Y train as well. So Y train, going to copy this one, same with the training, And I want to specify again that our data was shuffled already since the very beginning. That's why we're able to do this without any sort of random shuffling. If that wasn't the case for your data, shuffle your data before you do anything of separation of continuous variables versus categorical variables. And then finally, let's go ahead and get that test as well. Okay, so we have our categorical data, our continuous data, and then ytrain, ytest. So we can go ahead and check the length of these. So check the length of, for instance, categorical training, it's 48,000. Check the length of continuous training, and it should match exactly, so that makes sense. And then we can check the length of the test data set, and it's at 12,000. So again, this is 20% of the first 60,000 batch. Okay, so let's go ahead and set up our training model. So we'll say, I want to actually keep track of how long this takes to train. I'm going to import time and say our start time is equal to time.time. And then we'll say, go ahead and train for 300 epochs. You can choose less epochs if you don't want to train for that long. We'll keep track of the losses. And then say for I, in range epochs, go ahead and add 1 to the I counter. And this is essentially going to be exactly like we did before. We'll grab our prediction by passing in our training data into the model, both the categorical and continuous. We calculate our loss. We'll go ahead and calculate the square root. We'll take torch square root on the criterion between y prediction and y train. So we already have our predicted values here that the model is spitting back out. We want to measure our loss. So we'll measure it with root mean squared error. And then we'll go ahead and say losses, append that loss. And if we want to actually print out our progress, we'll say if I mod 25 is equal to 1. This will allow us to print out the loss at the very first epoch. We'll go ahead and say print f. And in fact, we can report more. Let's go ahead and print out a little more. We'll say I10. So say f, and then we'll say epoch is on I, and then loss is, and we'll go ahead and insert that loss there. Then we'll do the back propagation. Optimizer, go ahead and find that 0 gradient. Then move backward and say optimizer step. And then finally, we actually want to say how much time elapsed off of this. So we'll go ahead and calculate the time, and we can do this by doing the following. We'll go ahead and say time minus the start time is equal to duration, and then we'll print out something of the duration. We'll say training took duration, and duration is going to be in seconds, so we'll go ahead and say seconds. And if you want, you can divide it by 60 for minutes. Let's go ahead and do that, actually. We'll say duration divided by 60. Okay, let's go ahead and check this out. So running it, right off the bat, you should see the first epoch train. If you don't see that first epoch train after maybe like 10 seconds, then you may want to come back and triple check your code. But again, this is going to take a long time to train. We're dealing with a lot of data here. So we'll go ahead and fast forward in time and show you how long it took to train on my computer. So you can see here it's taken a while per epoch. And right now, we're not going that much lower in error, but hopefully you do see some decrease in error between your first epoch and your 11th one. We should see a significant decrease by the time we reach 300 epochs. I'll see you there. I'm going to fast forward in time. All right, here we are. After we kind of fast forwarded through time, after 300 epochs, we can begin to see that the loss starts to converge somewhere around this 3.3 or 3.4 range. It was actually still improving, but much less dramatically than in the beginning. So let's go ahead and plot out that loss function. We will say plt plot range epochs, and then let's go ahead and say losses. And we can then see here the loss throughout the epochs, and eventually we get this sort of convergence to somewhere around 3.3, 3.4. Okay, so let's go ahead and validate the model on our test set. So to evaluate on the test set, we'll say with torch, and we're not going to be editing our weights and biases, so we'll say no gradient here. We'll get the y values that are predicted from the model by passing in the categorical test data along with the continuous test data, and then we'll just calculate the loss. Remember, we're doing the root mean squared error here, so we'll say torch SQRT of our criterion, where we have y-val and then y-test. So we go ahead and run that, and now let's check out our loss. So it looks like our root mean squared error on the test set was 3.32. That appears to be in line with what we were getting for the training set, 3.38. So that's always good, and in fact this is at epoch 291. So there's still 9 more epochs, so we can see here there's probably some slight improvement on the training set beyond 3.38. So last thing I want to do is kind of print out the predicted values against the actual values and show you the difference for some of them. So what I can do here is maybe for the first 10 values, so something like for I in range 10, I'll go ahead and do this for the test data. We'll say print out, I will print out my y-val at I, and let's go ahead and say predicted, and let's just number these, so we'll also insert I here. So right now we have these predicted. Let's go ahead and grab that item so it looks a little cleaner. So I can see the prediction, and I can format this using a little bit of print formatting. 8.4f here is going to format that float to kind of be in line with a total of 8 spacing here, and then 4 points after the decimal. In fact, let's just do 2 points after the decimal. And then that's my predicted values. We'll go ahead and then say true value, and I will insert the thing for true, so that was y-test. Make sure that's a lowercase y. So y-test at I, go ahead and get that item, and there we can see the true. I'll format this as well. Let's say 8.2f. And so we can see the predicted values versus the true values. You can see on some of them we do have quite a large difference, but others are quite close. And if we want to calculate that difference, we can always just calculate it ourselves by saying something like diff is equal to, and I can grab the absolute value, so we'll say NP absolute value of y-val item minus y-test item. And then I'll also print that out as well. So then I can say the difference is diff. So we run that. We can also format that one as well. And there we go. So we can see a lot of these. Remember, our average root mean squared error is somewhere like 3.3. So we're doing pretty okay on some of these and then pretty off on others. But on average, our root mean squared error is 3.3. And here's just the raw difference between the actual values themselves. This is not the root mean squared error. This is just the raw difference between the prediction and the actual test value. Okay, so you just trained this model for a really long time. If you see here, it took me around 7 minutes, so that's pretty long because I have a really fast computer. But if you have a slower computer, it could take upwards of 30 minutes to an hour, or even a few hours if you're on a slower computer. So what we're going to do is we want to make sure we save this model. So what we'll say is torch.save, and we'll go ahead and pass in our model state dictionary, and let's call this taximodel.pt. All right, and that basically concludes this lecture series. We've shown you how to create the model deal with categorical continuous variables, set up the tabular model, and then not just train on a training set up here, but also then predict on a test set, and as well as saving our model. The last thing I want to mention is a really common question I get asked is, How do you use the model to predict on new unseen data? Well, recall that that is the test process. Right here, we literally just did that by passing in new unknown test data into our model and then having it get its Y prediction or Y evaluation. Now, the other thing I want to point out is in our lecture notebook, right now we're kind of all the way at save the model, but if you continue, we then kind of discuss how to load a saved model from scratch, something we already discussed before, but here we have the necessary code for it. You can create a new model and then just load up that state dictionary again, evaluate that model to get it running. And then what's also nice is another question students often ask me is, how do I predict on a single point of unseen data? And we've actually set up this little function here for you to play around with. It's called test data, and it takes in the model, and here it has a bunch of inputs and does all the pre-processing in a single cell that we did over multiple cells. So it creates that dictionary, creates those EDT dates, it grabs the categorical values from those date time objects, sets up your categorical columns and your continuous columns, stacks them, transforms them into torch tensors, and then using torch.nograd, it passes that into the model that you passed in, and then shoots out the predicted fair value. And so you can see an example here of running it, and then what is the pickup latitude? You would just put them in as a user. Okay, so that's it for this project. I hope you enjoyed it. We'll see you at the next lecture series where we're going to be dealing with the exact same data set, except then we'll treat it as a classification problem. And there's not a whole lot of changes we need to make for that. Thanks, and I'll see you at the next lecture.